Assalamualaikum class and good evening. So for today's class, okay, this is we go to the Thevenin and Norton equivalent circuit. So I believe that everybody already know about Thevenin and Norton equivalent circuit. So as we know in this chapter we do a AC analysis, right? So therefore, as I mentioned before, in AC analysis, we apply the same method as in DC circuit. So the only difference that's the number involved in the calculation is a complex number, right? So just some revision on Thevenin and Norton equivalent circuit. So Thevenin equivalent circuit, as we know, is actually we are represent our linear circuit in a form of your VTH and RTH, right? So this is not VTH, guys. Sorry. So this is actually your VTH, right? So VTH and ZTH, because this is a AC analysis, so we are using Thevenin impedance, right? So your VTH must be in series with your ZTH, right? So this is our Thevenin equivalent circuit. That's mean whatever our linear circuit can be represented with your VTH and also ZTH, right? So in Norton equivalent circuit, so we have a linear circuit also, but in Norton, this linear two terminal circuit represent by the I Norton in parallel with R Norton. So this is Norton equivalent circuit. So the relation between Thevenin and Norton, all right, can be found using this formula. So which is VTH can be calculated using Z and IN, and then your I Norton can be calculated using VTH divided by RTH. So, in this case, it's actually ZTH, guys. Sorry. So this one should be Z, right? ZTH. And then we know that the value of ZTH is always equal to the uh, Norton impedance, right? So this is how we relate between your Thevenin theorem and also Norton theorem. So, and then as we know, V Thevenin is actually V open circuit at terminals, and then I Norton is actually I short circuit at the terminal. Okay, so we go straight away to the example, right? So this is uh, uh, circuit. You are given a circuit, right? So if you see this circuit is already in a form of passive domain of frequency domain, right? So you have a voltage source over here, you have capacitor, resistor, and also inductor, and also resistor over here. So our aim is actually to find the Thevenin equivalent circuit at terminal AB. So therefore, this is where terminal AB are, right? So, uh, right. So in order to find the VTH Thevenin equivalent circuit, so we need to find the value of VTH and also ZTH, right? So we start with finding the value of impedance, Thevenin's impedance. Okay, so ZTH, which is ZTH can be obtained by setting the voltage source to 0. Okay, so that's mean you have a voltage source over here. So by setting the value of this voltage source into a 0 value, so that's mean we need to short circuit this voltage source. So therefore, uh, this is where we short circuit the value of uh, short circuit the your voltage source, and then this is the simplified version of the circuit. So if you see here, uh, 8 ohms is actually parallel with your negative J6 ohm, and then your 4 ohm here is parallel with the J12 ohm over here, right? So therefore, this is our terminal AB, right? By looking from this terminal, So we can say that this circuit is divided into two parts, right? So we can say this part as, we can represent this part as one impedance, and then we can also represent this part as another impedance Z2. So Z1 is actually 8 ohm parallel with negative J6, right? And then Z2, this part, actually your 4 ohm parallel with J12 ohms, right? So calculate this value, right? So this is when we combine Z1 and Z2, we know that ZTH at the end is actually Z1 in series with Z2. So what is the value of Z1, right? So Z1 can be found by using this parallel formula. So which is, you got here Z1 equal to 2.88 and negative J 3.84 ohm. And then Z2 is 4 parallel with J12 ohms. So therefore, you can get the value of Z2 equal to 3.6 plus J 1.2 ohm, right? So this is the value of Z1 and Z2. And then finally, you can combine Z1 and Z2 in order to find the value of impedance, Thevenin impedance, right? So this is how we did. Okay, Z1 plus Z2. So finally, Z Thevenin equal to 6.4x minus J 2.64 ohm. So this is the value of Z Thevenin, right? So after we got the value of Z Thevenin, so we can find the value of V Thevenin. So as we know, V Thevenin is actually V open circuit at the terminal. So the circuit shown here is actually the simplified version of the circuit, right? So this is the value of, this is where uh, the value of where is our VTH is actually, VTH is at terminal AB, V open circuit at terminal AB. So therefore, by calculating the value of current I1 and I2, okay, we can know the value of VTH, guys, right? So if you see from the circuit, all here is actually a parallel circuit. So that's mean voltage drop along this part equal to this one, and then voltage drop along this uh, part is actually equal to 120 with a 75 degree also, because all are in parallel. So therefore, if you got the value of I1 and I2, so we can also find the value of VTH, right? So therefore, from the circuit, okay, calculate the current I1 and I2. So I1, like I said, is actually the voltage drop across is equal to the voltage supply. So therefore, I1 is 120 with a degree 75 degree divided by 8 plus J6. So you got 12 with a degree 11.87 with a phase shift 111.87 degree, right? So and then I2, right? So I2 is over here. So I2 is actually our voltage source value divided by the 4 plus J12, which is equal to 9.487 with a degree 3.44 degree. So by knowing the value of I1 and I2, so and then we can calculate the value of VTH by applying a KVL around the upper loop over here, guys, right? So this one, right? Okay, by applying a KVL at this upper loop, okay, so I draw it here, right? So this one, okay, so you can calculate the value of VTH. So by considering this is your I1, this is your I2, so therefore the polarity for this for voltage drop at this capacitor is plus minus, and then for this one is plus minus, and then this is your VTH, right? So we write a KVL around this upper loop, right? So therefore this is what you got, VTH minus 4I2 plus negative J6 times I1 equal to 0, right? So elaborate this equation. So you got VTH equal to 4I2 plus J6I1. So plug in all the value of I1 then I2 that we already calculated, right? So this is your I1 value, right? So this is your I2 value. So therefore, at the end, you got the value of VTH equal to negative 28.936 minus J 24.55 volt, right? So this is in a rectangular form, but in a polar form, you can write VTH equal to 37.95 with a degree of 220.31 degree. So this is our VTH value, guys, right? So therefore, okay, you can calculate the value of IN, right? So using, remember this formula, V equal to IR, so I equal to VTH divided by ZTH. So therefore, you can get the value of IN, right? So hopefully you can calculate what is the value of IN. So this is how we did the analysis in AC. So basically, as I mentioned, we do a similar method in a DC analysis. I hope you, if you still if you still not understand, or you need to do some revision on DC analysis, right? So in order to understand, the only difference is actually the numbers that we use now is a complex number. The rest, all the method, we use the same method as in DC analysis, guys. All right. Okay.